Okay, welcome back to Real Analysis. If you have been following along, we just introduced the concept of compact sets last time, and we're doing a series of lectures on compactness to give you try to give you a sense of why this is such an important concept, but also give you a feeling for what compact sets are. Okay, and so today what I would like to do is talk about the relationship between compact sets and closed sets. Last time we saw that compact sets are, in some sense, small sets, right? They're the next best thing to being finite. Okay, so in particular, finite sets are compact. We also saw that compact sets are, in fact, bounded sets. That's what we proved last time. And what I want to show you today is that, in fact, compact sets are closed sets as well. But we're also going to see some other relationships between closed sets and compact sets. Okay? So that's the plan. And I want to just remind ourselves what a compact set is. So what does it mean for a set to be compact? A set is compact if every open cover of that set has a finite subcover. And usually we're talking about a set that's in some big metric space. So a set K in a metric space, let's say X, is compact if every open cover of K, where? In X, has a finite subcover. Where? Yeah, in X has a finite subcover. Now, what I want to show you to start off with is something I alluded to at the end of last time. That is, it really doesn't matter what space you're embedded in. That is, compactness is actually an intrinsic property of a set, and it is not actually doesn't actually depend on the metric space you're embedded in. Okay, and so that's the first thing I want to do for us. So let me have you also recall. So this is the definition of compactness, but also want you to recall what characterization we have for what it means to be open in a metric space. So imagine having a metric space, let's say X, and then maybe some smaller metric space Y. And we might ask, what does it mean to be open in X? Well, what does it mean for a set to be open? It means every point is a interior point. Or another way to say it is, every point can be perturbed a little bit and still stay inside the set. That's what it means for the set to be open, right? Okay, but last time we made a distinction then about what it means for a set to be open in X versus open in Y. You could imagine, for instance, a set like this, which doesn't contain its boundary here, but does contain all the points on the boundary here. What does it mean for this set? Is this set open in X? No, it's not open in X because you could be right on the boundary here and perturb a little bit and you'd leave, right? This point is not interior. There is no open ball neighborhood around this point that's still within X. Agreed? But is this set open in Y? Yes, because, okay, well here it's clearly open. You can perturb a little bit. But here, in Y, if you perturb it a little bit, would you still remain within Y if you only move within Y? Yes. Okay. Harris.
What about the endpoints on that boundary? So the places where the boundary, the little ball intersect with the boundary.
Oh, yeah. So I'm leaving these out in this particular example. But if these points, very good question. If these points were actually in the set, then this set would not be open in Y either, because you could march to the northwest direction here and leave the set. Okay, this point would not be interior if it were included. Okay, everybody with me? So this example here is an example of a set that is, in fact, open in Y. It's not open in X. But there is a relationship, as we saw last time. So the other thing we proved at the end of last time was we said, well, even if this set E is not open in X, if it's open in Y, it has a corresponding set that is open in X that's related to it. How? Just by doing what? Well, I claim that there's some other set that is open in X for which this is the intersection with Y. So that was the theorem from last time. We could call this set G if you wanted, which is the entire thing on both sides here. So the theorem we proved at the very end of last time was if you have E, which is a subset of Y, which is a subset of X, then E is open in Y if and only if, what? E is actually the smaller metric space intersected with some set G for some open G for some G open in X. So this is the correspondence between being open in a subset, a metric space that's a subset of a bigger metric space. Okay? Any open set over here corresponds to one over here. Could correspond to several, but it corresponds to at least one, right? And any set over here corresponds to one over here just by taking the restriction to Y. Okay? That's what we showed at the end of last time. And this insight is going to be the important ingredient in showing that compactness is really not dependent on the space you're in. If I want to talk about this set E being compact, whether or not I choose to talk about compactness in Y or compactness in X, it's the same. Okay? Let's see why that's true. I claim you actually already know enough to see why that's true. Now, of course, what we're really going to have here is some set K. You know, you might, for instance, imagine some set K here. And I might want to know, is this set considered compact? And so now the question is, what does it mean for it to be compact? I need to show that every open cover has a finite subcover. And if I want to talk about compactness in Y, then it better be an open cover in Y. Oh, so then I'd use what kinds of sets? Purple sets or yellow sets? Yellow sets to cover this creature. And I want to know, is it true that if it's compact here, is there some relationship between being compact in X, which would involve covering by purple sets? Okay, in fact, the theorem that we're about to prove says, in fact, the notions are equivalent. So if Y is, let's say Y is contained in X, they're both metric spaces, then the claim is K compact in Y is equivalent to being compact in X. And so you can always just stop talking about which metric space you're in. Okay, let's try to prove this. Which direction would you like to go first? Well, I don't know. How about the forward direction? So we're going to assume, what is the forward direction? What's the hypothesis? We're assuming that K is compact in Y. That means given any cover of this red set by yellow sets, I can find a finite subcover by yellow sets. With me? That's what I'm allowed to use if I need it. But that's a different question than asking, how should I start this proof? I want to show what is compact in where? Good. So I should start with a open cover of K in X. Okay, it's very tempting, I know, to start with an open cover of K in Y, but that's not where I need to start this proof. If you want to show that K is compact in X, you got to start with an open cover in X. Does everybody get this point? I can use the fact that at some point, if I have yellow sets, that I can take a finite subcover. But I'm trying to show that when you start with an open cover by purple sets, that there's a finite subcover. Okay, good. Here we go. So let's start with, suppose we're gonna assume that K is compact in Y. This is sort of in the background. Okay, I probably didn't even need to say it. I just wanted to remind ourselves, as we need it, we're going to use this fact. But the place to start the proof. So you should start with. Okay, this is not really part of the proof, but this is just to highlight. This is not the place that sometimes you're tempted to start, but this is what you're being asked. We're going to start with what? Consider an open cover of K in X. So let's give it a name. Consider, let's say, an open cover. U is often used for an open set. U sub alpha of K in X. This is an open cover in X. U here are purple sets, like that picture up there. Okay, and alpha just means arbitrary open collection. I'm not bothering to write the index set, but could be possibly an uncountable collection. Okay, I have an open cover of K by a bunch of purple sets. Help. I want to show that the purple sets have a finite subcover. How am I going to do that? And all I know is that if you have yellow sets, you can find a finite subcover by yellow sets. Help. Okay, now does everybody agree with that? That maybe a natural thing to do is to take all these purple sets and look at their restriction to Y. Those would be the equivalent of yellow sets, yes? Now what should I do with those yellow sets? Take a finite subcover because we know K is compact where? In Y. Good. Now I have those yellow sets. What do I do with them? I have finitely many yellow sets. And I want purple sets. Good. There's G's that complete the yellow sets. That is, that there's this correspondence. Everybody happy with that? So we'll just write that down. Consider an open cover by U sub alpha of K in X. And let's let V sub alpha be U sub alpha intersect Y. And now you're just going to tell the reader, then, V sub alpha cover are an open cover. I'll just write this for shorthand. V sub alpha cover what? K in Y. All covers are open covers. That what we're going to refer to, so I'm not going to write that down. But, yes, Willie. Yes. Oh, yes. Yeah. K is contained in Y. Thank you. It is a subset of both Y and X. Right. Otherwise, it wouldn't even make sense to talk about K being compact in Y, because it should be a subset of Y before you even talk about compactness. Yeah. Thanks for clarifying. Okay. Good. The V sub alpha cover K. Is that clear that they cover K? Yeah. Because K was in Y, and I see why Willie was concerned here. This is the point at which you need to recognize it. Mm-hmm. Right. That's right. Okay, very good. Oh, okay. So there exists a So probably should tell the reader this is by compactness of K in Y, there exists a finite subcover, which we can denote V sub alpha 1 through V sub alpha n. Nice. So we're just turning our intuition into a proof. So now help me finish this statement, this proof. What's the finite subcover that you are expecting to use now? That's purple. Remember, these are how many V's? These are the V's. Okay. So then what? We should go back to the original what? U's. Which U's? The ones that are indexed by the alpha 1 through alpha n. Okay. So then the claim is that the U sub alpha 1 through U sub alpha n cover K in X. That finishes the forward direction, doesn't it? As desired. Oh, and of course, maybe you should remind the reader that these are a finite cover. Finite cover of K in X as desired. Okay? It's finite subcover, a subcover of the original cover. Okay? That's important, right? You want your resulting sets to always be a sub-collection of the original collection. Okay, that's the forward direction, assuming compactness in Y. We showed compactness in X. How about the reverse direction? We're going to assume compactness in X, show compactness in Y, so I should start with what kind of sets? What kind of cover? Cover of K in Y. Very good. I won't redo this whole argument, but just remind you that here we're going to consider, so the starting point is consider an arbitrary open cover of K. I'll give it a name. Let's start with V's. That's convenient. V sub alpha of K in Y. And now we want to show there is a finite subcover. Okay, let's talk through this argument. It's very similar. I won't write it all down, but let's just talk through it. I start with a bunch of yellow sets covering K and Y. I want to find a finite subcover. So let me hear from someone I haven't heard from yet. What should I do? Bunch of yellow sets. Katie? Excellent. By this theorem. Okay, good.
And then that forms a cover of K and X.
Excellent.
And since it's compact in X, we can have a finite subcover of it.
Good. So you're saying every element of the cover corresponds to a bigger purple set that's open in the bigger space X. That's an open cover. It has a finite subcover. And now restrict to get yellow sets. And that's a finite subcover, the original collection. Everybody happy with that? This is a great time to ask questions. So consider an open cover V alpha K in Y by the theorem, the earlier theorem. There exists U sub alpha such that U sub alpha intersect Y equals V sub alpha, and these are open U sub alpha. U sub alpha, I said I wouldn't write it, but I'm writing it. That's okay. These U sub alpha cover K in X. So there exists a finite subcover. etc., etc. I guess I'll let you finish the argument. But now you want to, well, I'm almost done. I'm just going to write it down. So there exists a finite subcover, which we're going to call, help me, everybody should be able to do this now. U alpha 1 through U alpha n. Then, okay, this is enough for a sketch. V alpha 1 through V alpha n are a finite subcover of the V alpha for k in y. Are we happy with that? Good enough sketch of the argument. There are a few things to check. If somebody really pressed you, you might want to explain why this clearly still covers. Okay? But I'll let you worry about that. All right, excellent. So, what's the moral of the story here? The moral of the story is compactness is an intrinsic property of a set. It doesn't depend on what metric space you're embedded in. Just got to be one that contains that set. Yes,
So
Willie.
it can be, correct me if I'm wrong, a set could be compact in one metric space, but then if you change the metric itself, it might not be compact.
Yes, yes. If you change the metric, then all bets are off. Yeah, and that's because we're always thinking of one metric space being embedded in another metric space and inheriting the same metric. Okay. Yeah. Excellent question. You change the metric, you're actually changing the metric space. Mm-hmm. Excellent. Okay. So let me write this down so it at least gets in your notes. Compactness is an intrinsic property of a set. That's really what we're trying to say. Obviously, in some metric, in some space, but it's intrinsic. You can enlarge the metric space using the same metric, and it's still compact. Okay, so now we're ready to prove some other things about compact sets. We still don't have many examples of compact sets, but we're getting there, okay? Ultimately, we want to show that the interval, the closed interval that we encountered last time is compact, but we need some ingredients before we do that, okay? So we've shown that compact sets are bounded. It's also the case that compact sets are closed. Obviously, we're referring to some particular metric space being closed in a particular metric space. Okay, so, gee, why is this true? Why is this true? Let's draw some pictures to see if we buy that. Here is imagine the whole board is the metric space, and here is some set K. Oh, let's have a little more fun. Here is some set K. Okay. And it's a car. It's a compact car. And I want to show that this set, compact sets, are closed. Okay, so here's K. Okay, now, how do I show that this set is closed? What's one way I could try to do this? Well, let's see. What does it mean to be closed? A set is closed if it contains all its limit points, or, alternately, a set is closed if its complement is open. Which of those characterizations do you think might be most helpful here? Complements are open. Why do you think that might be more helpful when you're dealing with a definition concept like compactness? It's talking about open covers. Okay, so let's try that strategy. I want to show the complement of K is open, yes? So, this is one of the most fun proofs in this class. This is just so much fun, okay? So I want you to just be ready to appreciate this. Okay, here we go. We're going to take any point outside of this set and show that, what? There's a ball around it, a neighborhood around it that misses the car. Okay? That's our goal. So let's imagine that we have a point, P. How can I produce an open set that misses the car? And just for a little bit of comparison, I'll do a little scratch work here. I mean, you could imagine, for instance, another set like this. I mean, here's another set in the plane. Maybe, yeah, you could imagine, another set that's like really wild, perhaps, like this one. So this is like a set that's sort of going off to infinity in both directions. And here's a point, right? This is not a bounded set. And so we know, since compact sets are bounded, this is not a compact set, right? That's another kind of example we could be looking at. And this is, of course, the example we want to focus on. You could also imagine, for instance, a set that looks like it might have no boundary, and a point right that's not inside. And this clearly doesn't have a neighborhood, does it? Okay. Okay. Yes, Jenny? Oh, interesting. Interesting. Okay. So Jenny's saying somehow we want to use the fact that every open cover is a finite subcover, so we need an open cover of K, yes? Okay. I want an open cover of K, and, well, how could I do that? And then, of course, I'm trying to produce a neighborhood around P that completely misses K. So how can I do that? I like your idea, Jenny, so let's just see what could we do. Would you agree that if K were a point, this would be easy? Yes, Maya? Why? Okay, good. If I had a particular point over here, let's call it Q, would you agree it would be very easy? Let's make even Q a little farther here, in fact. P and Q, you could find an open ball around P that completely misses Q. Would you agree? Yeah, it might be this one. Right? If this distance is 10, you might make this radius 5 just to be away from Q. Now, of course, you see this car here, and you're worried, right? You're saying, "Gosh, no, it's too big." Okay, but a priori, we don't necessarily know that much about this, except I know 2 points can be separated. Yes. Now, in fact, I claim something more is true, that not only can P be separated from Q, but I can separate both of them with disjoint open balls of radius half the distance between the two. Would you agree? Yes? Okay. So then what? How do I pass from one point to infinitely many points? What's the problem here so Maya said, take half the distance between P and Q. Maybe I'll do that, take those distances for every point in K and then take their minimum. Well, If there are not finitely many points, then what's the problem with taking the minimum of all those distances? May not, well, if it exists, it might be 0. It clearly exists. The minimum doesn't exist, but the infimum exists because it's bounded below by negative numbers, right? But that infimum might be 0. So look at this example. Would you agree that if I have a point Q, yeah, I can take a ball of radius half the distance between the two, right? And then I could take the minimum of all those things. But this is a case where, depending on how close Q gets, that minimum might be 0. That infimum might be 0, and the minimum may not exist. Okay? So, yes, you have an idea. Uh-huh. Okay. Okay. So, so it's certainly that the intuition is correct. That is, if you have a point here, and the infimum of all these balls were 0, then P would be a limit point. But we're trying to show that. So then what would that mean? Suppose P is a limit point. Then what? Right, we're not assuming it's closed. You're trying to show that it's closed. You're trying to show that can't happen. Right? Yeah, so this is your intuition is right, but it's not going to help us show that this set is ultimately closed if it's compact. We need to use compactness somewhere, right? Okay, but good intuition. So help. Let's see. Do we have an open cover, Steve? Uh-huh. Okay, I'm not sure what you mean, but let me draw some pictures here. Some more colors. Let me hear from somebody I haven't heard from before. Any other ideas as to what cover I might use for K? And I've just suggested that instead of just looking at distances from P, you might look at balls around Q. Yes, Patrick? What size? Okay. Well, would you agree, Patrick, that for any particular point, I have a ball like this that completely misses a ball over here? Yes? Yes? So let's give it a name. How about calling this set the set around P that misses Q's ball, U sub Q, and the set around Q that misses P's ball, V sub Q. Yes? And you could take this to be half the distance between the two. Of course, depending on the point, this Q has this ball, this Q has this ball, but this particular Q, let's call it Q prime, has a smaller ball, right? So the radius may change depending on the point, yes? Okay, so for every point, there are partner sets that separate that point from P. Call them U, Q, and VQ. Julian? Use what as a cover? The set of VQs is a cover. Yes, it is. So what? There's a finite subcover. So what? So we're here at this point, would you agree we're just following our nose? Not sure exactly where this is going, yes? But Moira is thinking, when I have a finite subcover, I have a finite number of these balls. And Jing Jing is smiling because she may have some insight here too. Yeah, you could take the balls over here. There are finally many balls here. Finally many balls here. Partners, yes? You could take the one of minimum distance. Why does that minimum have to be bigger than 0? Why does it have to exist? There are now finitely many distances you're talking about. Why does it have to be bigger than 0? Because it was bigger than 0 to begin with. All these numbers were bigger than 0, yes? And now we've used finiteness. Right? We basically have finiteness where we didn't have it before. That's what I mean when I say compact sets are next best thing to being finite. Right? We're actually appealing to finiteness here. Okay, so let's write that down. We're in really good shape here. So, proof. Just put this down carefully. So, we'll take a P and K. We'll consider, let K be compact. And we'll let P not in K. We'll consider P not in K. And we want to show, we'll show P is not a, P has an open ball around it. That's probably a better way to say it, right? So it's not a limit point or has an open ball around it. P has a neighborhood that does not intersect K. Not intersecting K. That's the same as showing P is not a limit point of K, which would also show, any point that's not in it, it's not a limit point, so K contains all its limit points. Or it's the same as showing that the complement of K is open. Either way, would you agree? We're done if we can do this. Yes? Okay. I might as well put this. So P is interior to K complement. Okay, so K complement is open. This is true for all P, then K complement is open. Okay, so what did we say? Well, for any Q in K, and notice that when here's the intuition. Now I'm writing up the proof. I don't need to give the motivation. I just need to start saying what these sets are. So for every point Q in K, we're going to let V sub Q be a ball, a neighborhood, of radius what? Yeah, I'll just write R over 2 first, and then I'll tell people what R is, around P. I'll let U of Q be N sub R over 2 around, do I have this backwards? This one's around Q. This one's around P, according to the diagram, where R is the distance from P to Q. Okay, this is the key sets. And then what we'll notice is what? The V sub Q, I think that this was Julian's insight, the V sub Q are what? Cover, they're an open cover of K. So, by compactness of K, there exists a what? Finite subcover. Let's give it a name. V sub, this is where you subscript the subscript. Ah, yes, Q what? 1, dot, 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 V sub Q N, little n. Oh, very nice. Help. Now what? So what should I do with the U's? Look at their partners. These are partner sets. So look at all the U's and take their. You could take the minimum radius. An easier way to say it is to take their. You've got a bunch of concentric balls. Take their intersection. That's probably easier way. Then let's give that intersection a name. Let's call it W. If we take the intersection of the U sub Q1 intersect U sub Q2 dot 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 U sub Qn. What can I say about W? It's the intersection of how many things? Finitely many things. Therefore, it's an intersection of finitely many open sets. It is open. And if you really want to help the reader, you could say in its radius, it's a ball of radius, the minimum of distances between P and Q sub I. That's one observation you could make. Okay? There's another way to think about it. Okay, now what do I claim about W? So now I had all these partner sets here. And the smallest one is the one I'm interested in. That's a ball, but why does it miss the car? Because VQ is a cover. Okay, but why does this ball miss the car? Ah, yes. This creature is disjoint from, well, it's disjoint from, this circle is disjoint from its single partner. But what about, how do I know it's disjoint from all the things that cover this creature? Okay, triangle equality will be useful, but give me intuition. Why is it that this point, this disk, misses all the other, so here's another point. Let me just draw another point here. And its ball. Maybe I should do a different color here for these partner sets. So this is the partner that has this one as its partner. Why is this going to miss all the possible things, not just the one that corresponds to this one? Yeah, the green ball is in every set here. And every U, this green ball is in every U, but each U misses each V. Okay? So the green ball cannot be in the union of the UV. So that's this is the part where it takes a little bit of work. So the claim is W intersect each UV, each VQI is empty for each I. And why is that? Because, well, it's easy to see now the way I've written it, because W is in U sub Q, right? U sub Qi. And U sub Qi intersect V sub Qi is empty. Okay? Everybody happy? All right. So we are done. Why are we done? Because I found the desired Q. Okay, so maybe I should remind the reader. So W is the desired neighborhood. That's probably what I should insert here. W is the desired neighborhood. And the word desired makes the reader think, oh, yes, you referred to something that you wanted to show earlier. Okay. Any questions about this proof? So really what we have is, it's sort of an amazing kind of idea here that I can separate P from each point. There are infinitely many points, but that's where compactness comes in. Okay. Beautiful, beautiful idea. All right. So what do we know? If a set is compact, then it must be closed. So we have, as a easy consequence, something that you've already seen, and that is, for instance, example 0, 1, this open interval is not compact. We have already seen an open cover that doesn't have a finite subcover, concentric things getting bigger and bigger and bigger, right? But now we can see from this theorem that it's also clearly not compact. Okay, if it's going to be compact, then it has to be closed. Okay. Okay, very good. What else can we say about the relationship between compact sets and closed sets? Compact sets are closed, but are closed sets necessarily compact? No? Give me an example. How about the entire real line in the entire real line? It's not compact because it's not bounded. That's one way to see it, right? So notice that the entire R in R is not compact because it's not bounded, though it is closed. So, closed sets are not necessarily compact. Or sets are not necessarily compact. Okay, Willie. If it's closed and not open, is it still compact? Well, excellent question. What about the set that goes 0? It's a ray starting at 0. Is that closed? Yeah, it's closed. And it's also not compact because it's not bounded. Excellent question. Yes, Emil. Ooh, excellent question. Are closed and bounded sets necessarily compact? We were going to answer that question next lecture, but since you asked, it'll turn out that closed and bounded sets are not necessarily compact it's not in every metric space, but it is true in R. Okay? And so that's something called the Heine-Borel theorem, which we will prove next time. And we're leading up to. Okay? Excellent question. Harris. That was exactly the same question. Yes, that's a famous theorem where we're going to show closed and bounded sets are compact in R, but not necessarily in every metric space. Yes?
For any set we pick, can we find a metric space in which it is compact?
For any set, can you find a metric space in which it is compact? Sure, yeah, you give me a set and put the for any, can you, right, so given the set that already has a metric, or you can pick the metric? Given a set?
That you can pick the metric to make it compact.
Okay. Well, yeah, so here's one thing you could do. You could ask yourself, what if I, yeah, that's a good question. And I should know the answer to this, but let me just think for a second. If you have a set, so I think the answer is no, but I need to think about that. Yeah. Certainly if you allow pseudometrics, that is, if you allow points to be distance 0 that are not the same, then the answer is yes. If you just define compactness by open covers, because then everything is just all in one ball. Everything's open, everything's closed, and it's compact. Every open cover is got a finite subcover just by that one set. Yeah. Excellent question. Let me think about that. Okay, and get back to you. Okay, so closed sets are not necessarily compact. But here's one thing we can say. So this is leading up to the theorem that Emil and Harris anticipated. If I have a closed subset of a compact space, then I can actually say that that's also compact. Of a compact set. So let's call the subset B of a compact set K, I claim is also compact. So we're going to take a couple minute break, and then after the break I want to prove this theorem. Okay. Hi.
I turned in my.
I got it. I got it. Thanks. Oh, just put it there. That's great. Thanks.
Are we supposed to hand in our readings for the third homework along with the midterm?
Yeah.
Okay.
Did you not do that?
I didn't realize. I just thought.
Yeah, I guess. Yeah. Okay. So, get them. Yeah. I'll make an announcement about that.
Okay.
By the way, I don't know if you guys checked the website, but regrades for homework 3 were actually due last week. Rewrites. If for some reason you didn't see that, we could get the graders to regrade them, but maybe you should just get them to me today, okay? And then in the future, please check the website. I know it's very easy to just use the tech files that people send around and not read the website, but please read the website, okay? By the way, I guess I should also say that this homework is actually the last homework in which rewrites will be allowed, since rewrites are actually basically a way to help you improve your writing, but hopefully by now you're beginning to understand what good writing's about. So this coming assignment is the last one which rewrites will be allowed. So try to write up this assignment as well as you can the first time, and try not to lean on the rewrite, just to see if to get good practice with your writing. Okay, let's resume. So before the break, we showed that compact sets are closed, and now we're addressing the question of whether closed sets in particular cases are compact, because they're not necessarily in general compact, but one instance we can say they are compact is if you take a closed subset of a compact set. So here's some compact set K, and if you have some closed subset inside B, then I claim B is also compact. And this is another fun argument with compactness. So I want to show what is compact? B. So I should start with an open cover of B. A lot of people are tempted to start with K, but no, you're trying to show B is compact. Let's start with an open cover of B. So here we go. Proof. Consider, or let's just give it a name. Let U sub alpha be an open cover of B. Okay, time to draw some pictures here. Here's an open cover of B, maybe by some sets here. Okay? Could possibly be lots of them. I won't draw them all. Okay? Now, I want to find a finite subcover of B using this collection. So find a finite subcollection. Yes? How am I going to do it? What do I know? I know K is compact. So if I'm going to use the fact that K is compact, I'm going to need to have an open cover of K. Do you see an open cover of K here? Ooh, okay. Maybe I'll use, okay, yeah, so certainly if I want to find an open cover K, there better be some relationship with these green sets, right? Otherwise it would be a dumb thing to consider, okay? So, good. Many of you are saying, let's use these sets. Okay. Well, they don't necessarily cover all of K, so what should I do? Add more sets, perhaps. Now, would you agree that if I add more sets, it might be a bad thing to add infinitely many sets? Because then when you take the finite subcover, you might not get any of the original green sets, right? Okay, so can you see an open set that covers, or some open sets that cover the things that we've missed? I'll give you a hint. B is closed. B is closed. Okay, let's see. Let me see. Raise your hand when you think you can see an open set that might, a set or sets you might use to cover everything else. Green sets cover B. I need something or some things to cover everything outside. I know that B is closed. Therefore, as Katie suggests, its complement is open. And what does it do? It covers everything outside of B, yes? Ah, okay, very good. Check this out. This B complement is everything outside of B, possibly more than K, but that's all right. We don't have a problem with that. This is B complement, and it's open. Do we have an open cover of K now? Yes. And K is compact. Therefore, it has a fun with open covers, fun with compactness. Yes. This is like, now we're just kind of following our nose here. Before we keep going, and you can keep going in your head if you want, I just want to write down what we have. Let U alpha be an open cover of B. Okay, we want to find a finite subcover. I won't write that down, but that's where we're headed. And now we're saying, notice, what? K complement is, B complement is open because B is closed. I won't write that down, but maybe we'll write it down, but by the end of the course, you probably won't need to write that down because you're assuming the reader is able to see why this is true, because B is open. So maybe this is worth putting in parentheses. That would be not true. Closed. Thank you. So, what? The U alpha union a set containing B complement is an open cover of K. Happy with that? Therefore, by compactness, there exists a finite subcover. What finite subcover? Help? Richard? Have an idea here? Okay. Are you sure B complement is necessarily going to be there? Good. Okay, good. So if the green set's covered all of K, B complement might not be needed, but otherwise it's B complement together with some things of U, of the U alphas, yes? So how do I notate those? U alpha 1 through U alpha n. And then we could just say possibly B complement.
Couldn't we just include it anyway because a finite number of things plus 1 is still finite?
Oh, very good. Let's just throw it in anyways, because it's still finite. There exists a finite subcover, which may or may not need to include B complement. We're going to throw it in just because. Okay, I like that. Everybody happy with that? This is a finite subcover of this cover. Is this a finite subcover of the original cover? Not necessarily, because it might have B complement in it. So you haven't finished the job here. Find me a finite subcover of the green sets that covers B. Julian? Excellent. B complement's not covering B anyways. You know it's not necessary for B. It might be necessary for K, but it's not necessary for B. Yes? So here we go. This is a finite subcover. And notice B complement. So we should be clear. This is a finite subcover of U alpha union B complement. Notice B complement does not cover B. How about this? Intersect B is empty. So the subcover U1, U alpha through U alpha n covers B because it covers K, right? Because it together with B complement covers K. And it's finite. And is finite subcover of the original cover. Everybody happy with that? Bonnie, are you happy with that? Looking good? Okay. Any questions? So what have we shown now? We've shown that small sets, if you take a closed subset of a small, namely compact set, it's still small, namely compact, right? Sarah's happy with that? Good intuition? Yes? Okay, excellent. Great. What else can we say about compact sets? Maybe it's worth at least remarking or making a comment about one of the corollaries of this fact. If you have a closed subset, a closed set and a compact set, not necessarily related in a metric space, in some big metric space X, then their intersection is going to be what? Picture here is, let me just erase this part. Picture here is you have F closed, K compact. What can I say about the intersection? It's going to be compact. Why is this a simple corollary? Good. K compact means K is closed. F intersect K is therefore closed because they're both closed. But then F intersect K is a closed subset of a compact set. Happy? And therefore it is compact. Okay. Very nice. Okay, great. So what I want to do is lead up to the Heine-Borel theorem, which we want to prove next time. But to do that, I have to prove a preliminary theorem, which will be needed for that fact. So we want to show that closed and bounded subsets of the real line are in fact compact. But to do that, we first need to show that intervals are compact, closed intervals are compact, which we haven't even done yet. Okay? So we've got to do that. But in order to do that, we need the following theorem, which is by itself an interesting theorem. And this theorem says that nested closed intervals in R are not empty. Okay, I don't know why I put a parenthesis around this, but because I was actually going to say it more formally, which I could still do. Nested closed intervals in R are not empty. I should point out that the same fact will be true in RK if instead of intervals, you replace intervals by K cells, which are boxes. K cells are boxes, closed boxes. They look like this in RK, in case you had any question about what the shape of a box is. But you take interval, cross interval, cross interval, etc. Okay? But you can see the book for that if you want. We're just going to do in R. And, of course, the picture is, what does it mean to be nested? Well, you might imagine, for instance, IN being marked by interval endpoints A and Bn. And nested means, what do you think nested means? Just take a wild guess. A1, B1, interval in between. A2, B2, A3, B3, A4, B4. Okay. Everybody happy with my characterization of nested? Okay, these are all nested intervals. Yes? All right. Now, the claim is there's a point in the intersection, point in all these sets. Can you see which one? I see Willie doing this, but what's that? Which one? Which point would you like to take? Well, how do you know there is one? Why is there a point in here? Between A4 and B4? And A5 and B5? Well, we're trying to show it's not empty. Thank you, Maya. Well, what limit point, what? Okay, you guys know enough from week 3 of this class to suggest a point that's in here. Give me a candidate. Give me at least a good candidate, and I'll give you a hint. A1, A2, A3, A4, A5, A6. Oh, supremum of the A's? Why does that supremum have to exist? It's a bunch of real numbers. They're in fact upper bounded by B1. Very good. So here we go. There's a point here. We'll call it X. So nested, let me just finish writing down what nested means. Nested means if M is bigger than N, then AN is less than or equal to AM, is less than or equal to BM, is less than or equal to BN. Everybody happy with that? And so now here's our proof. Very, very nice idea. Very simple. Let's let X be the supremum of the AIs. And it exists. We'll just tell the reader it exists because they're bounded by B1. Happy with that? We have a candidate. It exists. Now, explain to me why X must be in all these intervals. Is it clear X is at least bigger than all the A's? Why? It's a supremum. Good. So clearly, X is bigger than every A sub I for all I. Because it's the supremum, yes? Because it's the sup. That's enough for your notes. Why is X less than all the B's? This one you have to be a little more careful with. Why is X less than, and maybe one way to do this is, tell me why X is less than B52. Why is X less than B52? Okay. David?
Because B53 is also a bound on A, so that, for instance, x was equal to or greater than B52,
Uh-huh.
then that means that supremum is not in fact B52.
Okay.
B53 is less than that.
Okay, so let's see if we can write this down. And we're claiming x is less than bn for all n because by bn is an upper bound for all a sub m by, we'll call it Smiley, where Smiley is this fact. So what are we saying? You give me any b, I claim it is bigger than every a. And the reason is, you give me any b, like bn, it's bigger than every a because bn is bigger than, b52 is bigger than a52. But b52, if you want to show b52 is bigger than a100, well, you know b52 is bigger than b100, and b100 is bigger than a100. You can do that for any m. Okay? And so now this is enough to show that it's in all. So I'm just going to end the proof right here. Okay? And this is such a important concept. I just want to show you. I'm going to finish with now a very, very quick proof. This is an aside, but I'm going to give you a new proof, a different proof. Oh, this is so cool. New proof that R is uncountable. It's going to be one of those proofs where you go, what? What? Did you just do that? Using this fact. It's not in your book, I don't think, but this is so fun. Okay, here we go. Proof, R is uncountable. Well, suppose it were countable. Suppose R is just can be listed in a sequence. So it's countable. Okay, suppose it were countable. Are you ready for this? Because if you blink, you're going to miss it. Okay, yeah, suppose it's countable. Well, that's fine. x1, x2, x3. Okay, these could be hopping around here. Well, you can't stop me from choosing an interval, I1, in the real line. So these are intervals that misses x1. Would you agree with that? I can choose an interval. You certainly can't stop me from choosing an interval that misses x1. Oh, okay. Well, then I'm going to choose another interval, I2, that is in I1, so it's nested, but misses both x1 and x2. Well, clearly it's going to miss x1 because I1 did, but can I choose it so it misses x2? Yeah, sure. How about that one? Yes? Would you agree that I could continue this process, that I'll choose I3 and I2 that misses in addition x3? Why? Because I've got this interval, and wherever that point is, I can choose something on either side of it that misses it that's still a closed interval. Yes? So I have a nested sequence. By this theorem, there exists a point in all these intervals that is not on the original list. End of proof. There exists an x in all the I sub n in the intersection of I sub n, and x is not in the list. In the list. Done. Pretty nice. And of course, you'll have to step back and say, well, wait a minute, that was way too easy. So how was that? Where did we do the hard work? Because we obviously did hard work for the other proof, right? So where's the hard work here? Well, it's in there. It's also in, all the machinery we built up with Suprema, right? Okay, have a great day. Next time we're going to prove the Heine-Borel theorem, characterizing compact sets in Euclidean space.